Astra, it's your favorite middle schooler back for the next part of the space tour.
Oh, joy. Who are you again?
I was on your tour last week. I was literally the only person in the audience outside of that strange lady I summoned by saying Pluto 3 times.
Listen, kid, I give 3 tours a day. 5 if we're in extended summer hours. I don't remember everyone who comes through tourist TRAPPIST tours.
You remember? You threatened me by showing my doppelganger dying by falling into a black hole.
Oh, right. You were that annoying child with no guardian.
I was. Here I am, again, unsupervised, because I'm mature, independent, and really cool.
Good one. The tour will start in a few minutes, so go sit down.
Astra, you still have to do your pre-show announcements, and we're at time.
Quack.
Okay, I'll do a quick intro and then press play, okay?
Just give me the cue.
Welcome, friends, to the Black Hole Tour. I'm your space tour guide of space, Astra. We have a beautiful day here on TRAPPIST-1E, so thank you for spending it with us and choosing Space Expedition. Remember, you'll go a reasonable distance with Space Expedition.
Is this the same tour intro as from last week?
Please shut up. Now, this is part 2 of our black hole tour. So, if you want to join us for part 1, where we go over the theory of black holes, click the card above.
Starting with the ads early, I see.
But don't worry, Space Voyagers. The things we'll cover in today's video will still make sense if you didn't join us for part 1. Today, we'll be investigating how black holes are detected, the technology used to find them, and maybe, just maybe, I'll make it through some of this video without being heckled.
Unlikely.
Welcome to Bad Astra.
Fine, let's get to the science content.
Why?
We need to talk about polyamory.
Remember when Pluto was demoted to dwarf planet?
It's okay, man. We all make mistakes.
Isn't physics fun?
Is this being recorded?
In the last video, we covered how not even light can escape from a black hole. But if we can't see them, how do we even know they exist? How do we find them if we can't see them? Because black holes don't emit light, you can't tell them apart from the dark and depressing emptiness of space. To first detect the black hole anchoring our own Milky Way galaxy, in the 1990s, astronomers analyzed the motion of stars tightly orbiting Sagittarius A star, the radio source at the Milky Way's center. Newton's laws tell us that the mass of a thing can be calculated if you know the speed and orbital radius of the stuff orbiting it. If you know how fast and far out the orbiting stuff is, you know the central mass. If you measure those stars' velocities and radii, you can calculate the central mass. You can also calculate the maximum possible volume from the closest in orbiting star, since stars can't orbit inside a superdense object. You can further constrain the central mass's diameter by measuring how rapidly light from Sagittarius A star changes brightness. For all of Sagittarius A star to brighten, signals from the cause of the brightening must travel from one side of Sagittarius A star to the other. Since nothing can travel faster than light, Sagittarius A star can't be bigger than the distance light travels in the time it takes Sagittarius A star to brighten. Sagittarius A star takes about an hour to brighten significantly, so it can't be more than 1 light hour about 1 billion kilometers across. Combine that with an estimated mass of 4 million times the mass of Earth's sun, and odds are you have a supermassive black hole on your hands. Gathering these measurements and mathematically showing that Sagittarius A star was in fact a supermassive black hole is how Dr. Rainer Genzel and Dr. Andrea Ghez won the Nobel Prize in 2020.
So they won a Nobel Prize for not seeing a black hole? Does that mean I can win a Nobel Prize for not laughing at your jokes?
The difference is that they won a Nobel Prize for seeing all the evidence that points to a black hole. Like my jokes, the black hole is still there, even if you're not intelligent enough to understand the evidence that is, in fact, there.
Evidence of a joke does not mean it's funny.
And I do not get paid enough to deal with this. Observations have shown that our galaxy isn't alone in being anchored by a black hole. In the year 2000, not much has changed but the odd emission lines.
What are you talking about?
Oh, you're too young to know who the Jonas Brothers are, aren't you?
I'm sorry, I don't listen to ancient pop music.
You're lucky you're not on Jackie's tour. It's all bad classical music puns. Never mind. Before we could image black holes, the best techniques were indirect observations.
Like side-eyeing a tour guide that made a Jonas Brothers reference in 2021?
No. Like using a bunch of math, looking at the light around a black hole, and shutting your mouth on a tour. And it's 23:95 and we're on TRAPPIST 1E. Please just go with me, kid. Last tour, a child coughed on me after shouting coronavirus, like Cardi B, which is considered bioterrorism. And that was just the first show of the day. In the year 2000, Bradley M. Peterson and Omri Wand showed that the emission lines from active galactic nuclei suggested that there were supermassive black holes anchoring other galaxies as well. Remember, if you know how fast and far out the orbiting stuff is, you can calculate the central mass. But telescopes can't look at individual stars in other galaxies since they're too far away. So, to estimate the central mass of faraway galaxies, the observers measured the typical speed of the stuff in an AGN's broad line region, as well as the size of the entire region itself. The broad line region, in case you couldn't deduce this, is the region with broad emission lines, because scientists are very good at naming things. Getting the velocity is pretty straightforward, since fast-moving particles cause emission lines to broaden in a measurable way. Again, broad line region. Getting the typical radius is harder, since the galaxies we're talking about are really far away and the broad line region can't actually be resolved. This is where reverberation mapping comes in. When the background light from the black hole's accretion disk varies, the broad emission lines vary or reverberate as well. More specifically, the background radiation excites atoms, which in turn produce the line emission, so changing the background light changes the lines. However, this effect isn't immediate, since light takes time to travel from the accretion disk to the broad line emission region. That time delay between the changing continuum light and the changing lines tells you how big the broad line region is. Putting all the data together, Peterson and Wand used the emission line width to measure orbital velocity and reverberation mapping to measure typical orbital radius. These two numbers let you estimate the mass of the central object and give you a maximum size. When Peterson and Wand actually made these measurements on a few AGN, they got really big masses contained in a really small space, consistent with the presence of a supermassive black hole.
Sounds like a long way of saying they still didn't see a black hole to me. I think I'll go into science because I'm great at not actually seeing things.
Oh, I'm fully aware. I've tried to get you to shut up on this tour several times already.
See? Top-tier scientist right here. Might as well hand over the Nobel Prize right now.
Let's move on to gravitational waves and how they help us detect black holes. In the last tour and in our general relativity video, we learned how massive objects warp space-time, and that's how gravity works. Gravitational waves happen when a gravity event, something that causes ripples in space-time, like when you drop a rock into still water.
Or when you jump on your parents' waterbed, even when they told you not to, and you accidentally punch a hole in it, so you panic and put your mouth over the hole so it doesn't spill out any more than it has, but you're stuck there now with gross bed water in your mouth, no way of finding anything to actually stop the leaking, so you have to stay there until you can get the flex tape delivered, because the meme showed that it could be used to stop leaks. But leaving to get the tape from the front porch will lose water, and you're wondering how you're going to get out of it, and how you're going to get over his death. But you still have the waterbed to worry about, but the flex tape is on the porch, and you should fix your grieving heart in the waterbed, so you have to risk it anyway, run down to get the tape to slap its strip over the hole, and hope that your parents don't notice the tape or the more deflated waterbed.
I'm glad you're connecting the material to your life in very specific and strange ways. And jumping on a waterbed and how it ripples is kind of like gravitational waves. Yes, Space waves happen in space-time when a black hole merger happens because of the acceleration when they start going at it. That's when one black hole loves another black hole in a way that is low-key toxic and so codependent to the point where they decide they should just become one bigger black hole rather than allowing themselves to continue as two distinct individuals.
So the two space buttholes became one big space butthole and let out a giant fart wave. Got it.
We were so close to avoiding all butthole-related comments on this tour, but here we are. The way we detect these waves, and therefore the black holes, is with the tech at LIGO, the Laser Interferometer Gravitational Wave Observatory, and the Virgo Interferometer. That's just named after the Virgo cluster. They don't have a cool acronym. These interferometers were designed to detect gravitational waves. Each detector contains two long perpendicular evacuated chambers 4 kilometers long, with lasers being continually fired back and forth along both chambers, and a detector that can measure minute changes in the relative light travel times along the two paths at the intersection. Light should take the same time to travel the same distance, unless a gravitational wave came and changed the distances in one direction. A regularly oscillating change in distances signals the presence of a gravitational wave. LIGO, 2 detectors in the United States, and Virgo, 1 detector in Italy, are the 3 best rulers on the planet, capable of detecting distance changes as small as 1/10,000th of a proton. These fancy measuring tapes detect gravitational waves from black hole mergers and neutron stars. When they work together, the 3 LIGO and Virgo detectors can triangulate the signals they each see, and in 2017 were able to actually calculate the rough position on the sky of a neutron star merger, giving telescopes something cool to image, leading to a ton of new information. Though, if you had to choose which one to work at, you'll probably get a better quality of life and health insurance in Europe. Imagine walking out into the Italian afternoon after discovering amazing things with a Virgo, then smell the fresh Italian food everywhere, not having to worry about crippling medical bills that can drive you into poverty at any second in a for-profit medical system completely corrupted by corporate greed.
That is horrifying and not at all funny.
My existential dread and political commentary isn't a joke, it's just a cold, harsh reality. But back to the ha-has and space facts. Since black hole mergers can't be seen directly, we have to rely on the gravitational waves to tell us it happened. But neutron stars give off light that we can directly observe because they're so lit, fam!
Suddenly, I miss the existential dread.
What, are you not pogged for science yet?
I'm so glad I'm dead.
Astra? Are you okay?
Fine. But seriously, kilonovas, the explosions from the neutron star mergers we just talked about, are super cool. Stellar mass black hole mergers are super cool. Intermediate mass black holes are super cool. But even bigger mergers produce gravitational waves with longer wavelengths, and to detect longer wavelengths, you need longer arms on your interferometer. But building super long arms is expensive. What if, instead of arms, you just had lasers bouncing between 2 point detectors? Oh, wait, you need a vacuum. Which is why the arms are expensive. Okay, what if you put the detectors in space, where the vacuum is free? That's where LISA, the Laser Interferometer Space Antenna, comes in.
Ah, yes. The coolest possible acronym for the coolest possible set of huge space arms.
It's basically LIGO, but bigger and in space, with satellites that detect the ripples in space-time. LIGO has 4-kilometer arms. LISA's arms, formed by 3 formation-flying satellites, are functionally 2.5 million kilometers long. And they still need enough sensitivity to detect gravitational waves. And if giant super accurate space ruler doesn't get you excited, you're not nearly nerdy enough for this tour.
Oh, I've known since the first tour that I'm not enough of a nerd to enjoy this. Space ruler with the name of a middle-class white woman whose biggest loves include her husband, son, and cocker spaniel and works at a library just isn't cool.
Lisa is a great and supportive person and totally deserves a giant and accurate measuring stick in space named after her. But let's get back to black holes, since in 2019, we got a picture of one.
Hold on. Didn't you say we can't directly observe black holes because they don't emit light? But now you're about to show me a picture?
Yes, I am.
Look at this photograph.
It technically is the shadow of a black hole, but still. This was taken by the Event Horizon Telescope, which is the size of the Earth, involved a huge collaboration, and provided the image for the Bad Astra Kazoo cover album. As with most things in life, size matters. The bigger the telescope, the better the image you get for things really far away. Unfortunately, building a giant telescope the size of the Earth is a little tricky, especially in this economy. But there's a cheat code astronomers found. If you get a bunch of telescopes talking to each other, you can turn a group or array of telescopes into one giant telescope with an effective size of the two telescopes furthest from each other. Now, these Frankenscopes will have a lot of holes, but we can fix that in post. Sort of. Observers can use the rotation of the Earth to partially fill in the Earth-sized telescope's holes by waiting for the Earth to rotate and move the little component telescopes into new positions relative to the black hole they're trying to image.
You mean the rotation of the sun around flat Earth?
If you want to know more about why the Earth is round, check out our video, How Do We Know the Earth is a Globe?
Not another ad.
Then don't bring that pseudoscience conspiracy theory nonsense to me. You really think anything would remain on the Earth if it was flat? Gravity doesn't work that way. Cats would push everything off the edge. It makes no sense.
Astra, I think you need to take a break or something.
Whatever, we're back at TRAPPIST-1e, thanks Sagan. Thanks for flying with space expeditions where you'll go a reasonable distance. Come back next week when we talk about the 2020 Nobel Prize winners and their theoretical and observational contributions to our understanding of black holes.
Huh. Looks like flat Earth theory will end a tour real fast.
Astra out. Thank you so much for joining us here on Bad Astra. If you enjoyed watching, please like this video, leave a comment telling us what topic you'd like to see next month, and share it with everyone you know. Be sure to also subscribe and ring the notification bell so you never miss a new episode. And if you can't get enough of me, Eris, and Science Tommy, join our Patreon, where we post behind the scenes, deep dives, and other fun content. A special thank you to all of our Patreon supporters who make these videos possible. Astra out.